Hello, everyone. It is a great honor to make a presentation at this conference today. The title of our paper is, Real-Time VR Simulation of Laparoscopic Cholecystectomy based on Parallel Position-Based Dynamics in GPU. Our research team comes from the State Key Lab of VR Technology and Systems in Beihang University, Beijing Aerospace General Hospital, Stony Brook University and Beijing Normal University. This is the content we talk about today. In recent years, virtual reality, VR, based training has greatly changed surgeons' learning mode. It can simulate the surgery from the visual, auditory, and tactile aspects. VR medical simulator can greatly reduce the risk of the real patient and the cost of hospitals. Laparoscopic cholecystectomy is one of the typical representatives in minimal invasive surgery, MIS. Due to the large incidence of cholecystectomy, the application of its VR-based simulation is vital and necessary for the resident's surgical training. In this paper, we present a VR simulation framework based on position-based dynamics, PBD, for cholecystectomy. We investigate a number of soft tissue deformation methods, such as FEM, mass spring model, and PBD. We also study the simulation of electrocautery. Our research aim is to accelerate the deformation of soft tissue on GPU and improve the realism of fat tissue burning. The contributions consist of a deformation model of soft tissue based on graph coloring parallel acceleration, within the position-based dynamics, PBD, framework, a biothermal conduction model for fat tissue burning, and a hybrid multi-model connection method, which can simulate the separation of the gallbladder from liver in real time. This is the software architecture of our developed simulation system. It includes two phases, offline and online. The offline phase consists of loading the geometric model, initializing the physical model, creating stretching constraints and volume constraints, and coloring the physical model using the graph algorithm. For the online phase, the system first detects collision based on the data sent by the force feedback device, then calculates the potential distribution of the model and solves the constraints in parallel for the soft tissue deformation, and finally updates the model texture and shape in a graphic and tactile manner. The parallel PBD on graph coloring in our paper is described as Algorithm 1. For graph coloring, line 2 in Algorithm 1, we implement coloring partition based on the random dying disk graph coloring algorithm. The constraints are solved on GPU. Figure 3 shows the graph coloring of distance constraints. Each edge in the tetrahedron is a distance constraint, which can be treated as node. The blue point, in graph B, is abstracting the constraints with a shared vertex into two nodes, which are connected by an indirect edge. Two connected indirect edges denote these constraints having a shared vertex, hence they should be assigned with different color. This figure shows the results of graph coloring for the distance constraints and volume constraints. For the simulation of electrocautery, we focus on how to convert the heat into the potential distribution on the surface of soft tissue. We intend to update the temperature distribution of models based on the bioheat transfer equation. The surface bioheat transfer equation can be expressed as this equation. This figure illustrates the simulation of fat tissue burning process. The red point P1 indicates that its potential has reached the threshold T, boiling point. Consequently, the tetrahedron is in the heated state, blue edges, but the length is unchanged. P1 and P2 reach the boiling point, then the tetrahedron begins to burn. The red edge indicates that it is burning and the volume of the tetrahedron begins to decrease. P1, P2, and P3 reach the boiling point. Once the four vertices of the tetrahedron are at the boiling point state, the tetrahedron will be deleted. This shows the topology change of fat tissue mesh before and after electrocautery. Now let's see the experiments and comparison. This is 4 simulation videos of fat tissue electrocautery. This is 4 simulation videos of gallbladder and liver separation. This is the percentage of computational cost for each task during offline and online phases. The most time-consuming task in offline phase is the tetrahedron initialization, which takes about 2,886 milliseconds. The most time-consuming task in online phase is the parallel PBD deformation, which takes about 16.5 milliseconds. We also compare our graph coloring method with other approaches and in different models. We can see that random coloring disk algorithm is the most efficient method. This is the visual performance of different graph coloring methods. The left 3 columns are the coloring of distance constraints of different coloring algorithms. The right 3 columns are the coloring of volume constraints of different coloring algorithms. This is the comparison of parallel PBD and ordinary PBD simulation results for gallbladder model. The implementation of the coloring algorithm on the GPU can be 1.2 to 5 times faster than the algorithm on the CPU. We can find that this algorithm has a great advantage for real-time simulation. However, the improvement of performance using our dyeing algorithm is not as high as we expected. The main reason is that different groups of constraints are solved serially. The second reason is that the number of constraints for each color is not in good balance. It increases the calculation cost. This is the comparison of data size and computational efficiency with respect to the work of Kim. Our method is 3 to 8 times faster than his method. Our computation costs are significantly lower than it. And the advantage of our method is obvious when simulating complex models. This is the comparison of simulation visual performance with the work of Kim. We use dynamic texture techniques to render the process of stripping the gallbladder from the liver. During electrocautery with the L hook, the liver surface will leave burning traces, which enhance the visual realism. Finally, we invited 32 surgeons from Beijing Aerospace General Hospital to test and evaluate our simulator. All participants were asked to complete a survey to give us feedback. 82% think that we should apply the laparoscopic surgery simulator to the daily medical education. This is conclusion of our work. We used the random dyeing disk algorithm implemented on GPU to accelerate the deformation model and obtain a better computation performance. We also introduced a physical model based on bioheat conduction in the fat tissue electrocautery. Our simulator can separate the liver and gallbladder with a hybrid multi-model connection model. Nevertheless, there are certain limitations in our simulation. Due to the intrinsic shortcoming of PBD method, the stiffness of the organ model is sensitive to the number of iterations and the step size. But it could be eliminated with extended position-based dynamics, XPBD, which can be employed in our simulator in the near future. At present, Phantom Omni only supports single-point force feedback. A trainee can merely grab a point or a few points in local area when grabbing the soft tissue. To achieve more realistic results, we need to improve the haptic device to achieve multi-point contact. Moreover, we can develop the evaluation system, which can afford a reminder when operation error happens and deliver the score report after the training is completed. Thank you.